Okay, so fractals are pretty cool. They're just any shape with self-similarity, meaning there's a repeating pattern inside itself at different scales. I'm going to go over three: the Curlicue Fractal, the Koch Snowflake, and one in Pascal's triangle. And so the Curlicue Fractal is interesting because it uses an S value, which is an irrational number. And depending on the constant you choose for S, the fractal comes out looking differently because of how it's generated. So fractals are generated recursively using fairly simple steps. In the case of the Curlicue fractal, it adds 2 pi s to an angle, and so depending on the particular s value you choose, the Curlicue fractal comes out looking differently. And so you can see some examples here, like e pi, square root 2, etc. And these various s values make different Curlicue fractals, but you can sort of see though how they have this similar repeating pattern, and but yeah, depending on the s value, you get a different fractal. And so the Koch Snowflake, the next one, is pretty interesting. It's got a very simple pattern that for its generation. You can just try and figure it out yourself with each iteration. You can sort of see what's happening from here. You go to here, from there, you go to there, and so on. Theoretically, you get infinite iterations. It's not really worth going super far on the computer because there are only so many pixels, and past a certain point, it doesn't look any better, but that's okay. Anyways, so the pattern here, in case you didn't figure it out, is you take each side and you take this flat like sideline or whatever, and you replace it. You have the first third, and you replace the second third with like an equilateral triangle, and you take out this side, and then you have the last third. And then you do this to each side, including the ones you just made. So now that you just made like this whole shape, and then you apply that same process to each side of this shape you just made. So we apply that process to this one, to that one, to that one, to that one. And then for the next iteration, we'll do the whole same thing all over again, to there, and there, and so on and so forth. And theoretically, again, we have infinite iterations past a certain point, and the computer, it just doesn't look any better because the graphics are just not that great. And one interesting thing about this is theoretically, with infinite iterations, the perimeter should actually be infinite, even though the area is finite. And this sounds a bit counterintuitive at first. It's kind of weird. Like, how can there be infinite perimeter in this clearly like finite shape, right? It's all in this, screen. What's going on? Well, if you think about it, with each iteration, you actually increase the perimeter by 4/3, or you multiply it by 4/3 rather, like increase it by a ratio of 4/3. So the reason is you go from this side or whatever side. Each side goes from, if you imagine it's 3 units long, 1, 2, 3, to 1, and then this middle one being replaced by 2 units, so 2, 3, and then a 4. So the side goes from this to this, meaning you're multiplying the length of each side by 4/3, and so if each side is multiplied by 4/3, the whole thing's perimeter is multiplied by 4/3. And so the perimeter is the original perimeter times 4/3 to the power of the number of iterations. So with infinite iterations, you have 4/3 to the infinity, which will approach infinity. And so the perimeter will approach infinity. So, okay, there's an infinite perimeter. Well, clearly the area, though, that's not really increasing that fast. And well, okay, if you think about the area, what's happening to the area is you're adding more triangles, but these triangles are smaller. So the area equals the summation of the number of triangles you add on an iteration times the area of those triangles on that iteration. And this actually converges to a finite number, unlike the perimeter. The area is something like, I think it might be like 8/5 of the original area of the triangle. I'm not entirely sure about that. The point is, because the new triangles you're adding get a lot smaller, the area is finite. But the perimeter is actually infinite. And if this is sort of cool, but like in a mind-bending way, you can check out like Gabriel's horn and stuff, which are similar. Another problem is the famous one is the coastline of Britain, which if you measure with a mile-long measuring stick, is shorter than if you measure it with like a meter-long measuring stick, because you can get more of the details in with a meter-long measuring stick. And the shorter you make your measuring stick, the longer the coastline seems to be. And so what if you had like an infinitely short measuring stick? Would it be infinitely long? And so it's just something interesting to think about theoretically. Anyway, that's the Koch Snowflake. The last one is in Pascal's triangle. So first of all, there are two things you kind of need to know about this one. Pascal's triangle is generated by starting with 1 at the top, and then with each term below it, you add like the terms above it. And so the ones on the side, you just add the one to the right. But like if there's one that has 2 terms above it, you add the 2 terms above it. And so then the next thing you need to know for this one is mod division. And all this is taking the remainder. So like if a number doesn't go in evenly, it has a remainder. So like if you say, okay, what's 13 mod 4? The answer is 1 because, wait, yes, because, sorry, tired, because if you do 13 divided by 4, the remainder is 1, or 13 mod 3, the remainder is also 1. Don't think that the only numbers you can do this with are 13 and the answer is always 1. If you have 8 mod 5, the answer will be 3 because 8 divided by 5 has a remainder of 3. So that's mod division. It's just the remainder. And then this is when you combine Pascal's triangle with mod division, specifically of a prime number. But basically what's happening here is if you leave all the numbers divisible by 7 blank, what we're doing here is we're adding 2 numbers divisible by 7, and if you think about this, that's like 7 times a plus 7 times b. You can rewrite that as 7 times, in parentheses, a plus b. So obviously 7 is still a factor, which makes perfect sense. Whenever you add 2 numbers divisible by 7, of course, the sum is going to be divisible by 7 as well. And so if you think about it, if you have this long line of numbers all divisible by 7, their sums are all going to be divisible by 7 all the way down through this triangle. And so that creates these patterns. If you shade Pascal's triangle based on numbers divisible or not divisible by 7, what you actually get is a fractal called the Sierpinski Carpet, which looks kind of like this. And it depends on, as well, what number you use. But as long as it's a prime number, it looks generally like this. And you can kind of see it's a fractal because there's repeating patterns, so it's got that self-similarity where, as if you were to theoretically zoom in or zoom out, you would see the same thing come and be repeated. And I think that's about it. Obviously, I don't mean that's about it in terms of fractals. There are tons of other famous ones out there, like the Mandelbrot set or whatever. And they're pretty cool because you can calculate them fairly easily, recursively, and play with them. Here are just some interesting ones. Anyways, yeah. Oh, yeah. Okay.